Hi friends, welcome back. This is the second lecture on the compensator and controller. Last time we discussed about the lead compensator and the lead compensator, the basic. Again I'll tell you the transfer function. What we have seen in the last class is 1 plus s tau 1 divided by 1 plus alpha s tau 1. Okay, or simply write it 1 plus s tau divided by 1 plus alpha s tau. Okay, now this is the transfer function of the lead compensator we have seen. And what lead compensator will do, lead compensator will add 0 near to the origin. Pole will come after this, but near to the origin you have 0. Okay, and the lead compensator was high pass filter, or working like a high pass filter. We have seen the diagram of this also. Now we'll see the effect of lead compensator to the system. So the first is the lead compensator adds finite 0 near to imaginary and pole away from the imaginary axis. Okay, finite 0, very important point, and finite is pole away from the imaginary axis. Okay, this is the first point, you know very well. Now an LC or a lead compensator is HPF, high pass filter. Hence bandwidth of the system is very high. Obviously if you have high pass filter means you have high bandwidth, isn't it? You know very well what is the bandwidth all about. The next point is, as bandwidth increases, T rise decreases. Yes, because we have seen in the formula of T rise, or time is inversely proportional to the bandwidth also, you know very well. The multiplication of T rise and bandwidth, you know, constant. Okay, so bandwidth increases. Why bandwidth increases? Because high pass filter. So definitely your bandwidth is going to increase. Okay, so T rise decreases, hence transient performance increases. T rise means the time taken by the system to get its, you know, wait a minute, I'll show you. If this is the system output, this time is nothing but T rise, isn't it? Now the bandwidth is increases, the T rise decreases, this rise time is going to decrease, means your next waveform will be, let me change the color, your next waveform will be like this, isn't it? So if your waveform is like this, it means your T rise is going to decrease. T rise is going to decrease means your transient performance increases, isn't it? Next point is, an LC increases damping ratio, hence percentage of peak over decreases. Okay, so this is the point. The lead compensator increases damping ratio, so percentage of peak over decreases. Yes, definitely, as the zeta is going to increase, your peak overshoot is going to decrease, isn't it? Okay, perfectly fine. The next point is, an LC increases or improves the GM and PM. Yeah, definitely, when it's going to affect the transient performance, it means it's going to affect the GM and PM directly, gain margin and phase margin of the system. Why we are looking for the gain margin and phase margin for the system? To conclude the stability, isn't it? So GM and PM both are terms related to the stability. Okay, now it decreases the settling time, means the system will settle earliest, means it will settle very fast, isn't it? So the kind of delay or sluggishness in the system will be removed by lead compensator or not, tell me. The lead compensator makes system smart or more active. Okay, So in inverse of this, the lag compensator will do, or add some sluggishment into the system, isn't it? You are getting me? The next point is LC is similar to PD. PD we'll talk about later. The lead compensator is similar to the proportional derivative controller. Proportional derivative controller is nothing but the high pass filters, kind of. Okay, and you know very well the lead compensator is also the high pass filter. So both are similar in nature. Lead compensator is HVF, hence noise can enter into the system. Noise can enter into the system, so signal to noise ratio is very poor. See, signal to noise ratio. Your bandwidth is very high, so noise can enter into this. So noise is very high. It means signal to noise, if this thing is very high, this ratio will be very low or not. So signal to noise ratio is very poor, and for any system this is the desired quantity, that your signal to noise ratio should be very high, but here it's very poor. So this is disadvantage of the lead compensator, that the system is going to affected by noise. The very next point is the lead compensator creates, that's just this nonsense, attenuation in the system. To eliminate attenuations, we add an amplifier to the system. We have seen when we developed the transfer function formula, we were getting some alpha quantity outside of the magnitude, that is nothing but the attenuation. What we were doing there, we were putting one amplifier in the series, and that amplifier, the amplification of that amplifier is 1 by alpha. 1 by alpha is going to multiply with whatever you got there, and the alpha in numerator divided by alpha in denominator, you are getting the transfer function that we have seen, the standard transfer function 1 plus s tau divided by 1 plus alpha s tau, isn't it? Okay, so these were the effects of a lead compensator, very well. So the basic points related to lead compensator are: the lead compensator is the high pass filter, the standard format or standard transfer function of the lead compensator. Again and again I'll write over here. This is the standard format or standard transfer function of lead compensator. Lead compensator is nothing but high pass filter, isn't it? And this all points you have to remember. For the IES people, these points are very important, because there are so many questions in the examination in your previous year papers. If you observe in control system, compensator and controller, there are so many questions from this. Okay, now let's come to the next, and that is lag compensator. So what is the definition? If the sinusoidal input applied to a network, it produces the sinusoidal steady state output having phase lag with respect to input, then the network is the lag compensator. Say you are going to apply something to the system, means sinusoidal input, okay, and let's take its phase is 0, but when you are going to apply that to the lag compensator, at the output whatever you are getting, the phase of that system will be lagging. Okay, so here you can see this is the lag network. Okay, so you have to find out the transfer function of this. So I'm writing here directly the main transfer function. We have to remember 1 plus tau s divided by 1 plus beta tau s. It's similar to the the lead compensator. There we have seen this is for the lag. This is for the lag, and for the lead we have seen is 1 plus tau s divided by 1 plus alpha tau s, where this alpha is lesser than 1, but here in this case this beta will be greater than 1. Okay, so for lag compensator, if we'll talk about, so what we will get is, here the pole will be near to the origin and 0 will be away from the origin. You can see by this transfer function. Okay, let me take it over here. The transfer function of the lag compensator is given by 1 plus s tau divided by 1 plus beta s tau, isn't it, where this beta is greater than 1. Okay, and for the lead, what we have seen, I'm just comparing so it will be easy to remember for you. The transfer function is 1 plus s tau divided by 1 plus alpha s tau. Okay, where this alpha is less than 1 in this case. So when you will draw this, check the poles and 0 location on the plane, what you will get is, see here, the 0 is equal to 1 minus s tau. Okay, and what about the pole? The pole is 1, it's minus beta tau, and as I told you, this beta is greater than 1. Let's take suppose 2. So minus 1 by 2 will become minus 0.5 by tau. Okay, and this will be minus 1 by tau. So 0 is going to be away from the origin. So definitely here is the 0, but this pole is coming closer to the origin. Okay, so this is the lag compensator 8, one pole near to the origin and 0 away from the origin, isn't it, the standard transfer function. And for the lead compensator, if I'll write here, it will add 0 near to the origin, pole away from the origin. Okay, now let's come to the Bode plot for the lag compensator. The Bode plot for the lag compensator, the transfer function here, what we have seen is 1 plus s tau divided by 1 plus alpha s tau. It's beta. Okay, now first you are getting pole first you are getting, and then you are getting on the scale 0. So first you will get minus 20 dB per decade. Suppose here I'm showing here to you, here you are getting first your pole, and that is beta tau, isn't it? So I'm writing like this, minus 20 dB per decade, 20 dB per decade you are getting. Okay, and at exactly 1 by tau. In terms of frequency, if I'll write like this, you will get plus 20 dB, it will become flat. Okay, it will become flat. So now you can shift this origin, suppose, or this baseline, it will be like this, isn't it? So it's kind of which one, the low pass filter or not? Low pass filter. You will draw the transfer function by whatever I have told you how to draw the Bode plot. You will get the same thing, the low pass filter. Okay, now for the lead compensator, we define the WM, isn't it? Here I'll get WM. These two are the corner frequencies, omega 1, omega 2. There we have seen this omega m is nothing but under root of omega 1 into omega 2, isn't it? So here also the thing is same, omega c1 into omega c2 under root. This is your omega m. In this case, your omega c1 is 1 by beta tau into the next one is 1 by tau. Like this you have to do, isn't it? See friends, the multiplication of this s given here, it's tau, it's b tau, and a standard format in the transfer function of Bode plotting, what I have told you, you will make it like 1 plus s omega 1, 1 plus s omega 2. So directly we can fetch the frequency, because in terms of frequency we are talking about. Okay, so just make it, this is tau, it's given, but if you need in form of frequency, it's 1 by tau, isn't it? it will go down and it will become 1 by tau. See, 1 by tau is nothing but your frequency. So it's become 1 by tau, 1 by beta. Very important formula. You have so many questions based on this. And if I'll talk about the maximum phase, so maximum, you can draw the phase plot also. I'm leaving for you. Okay, though that is not important. Or so directly I'm writing for you. The phi m is something but sine inverse beta minus 1 divided by beta plus 1. Okay. There in the lead compensator we have seen phi m, that is for lead. I'm writing here sine inverse 1 minus alpha 1 plus alpha. Okay. What is the intention? The phi m should be positive, means beta should become here. Why? Because beta is greater than 1. So this entire term will be positive. Here this entire term will be positive. Okay. So like this you can remember. Okay. Now we'll come to the effects of lag compensator. It is LPF. Definitely lead compensator is your high pass filter working like as high pass filter. The lag compensator will work as a low pass filter. Hence the noise is filtered out. Yes, this is the the advantage of this lag compensator, that it will filter the noise. So noise is filtered out from the system. Signal to noise ratio is improved. The second point is it is low pass filter, hence bandwidth decreases. Now you know very well in the series all this bandwidth decreases, the rush time will decreases, the settling time will increase, sluggishness into the system will increases, kind of. See, as bandwidth decreases the T rise increases. Yes, definitely we know the T rise will increase and system response become very slow. System becomes slow, isn't it? This is the effect of lag compensator. Okay, now improve the steady state performance. See, this is the very crucial point. See, in the lead compensator what we have seen, the lead compensator will improve transient behavior. This will improve transient behavior, but your lag compensator will improve the steady state performance. Okay, and for any system, steady state performance is very crucial. Why? Because we are dealing with the steady state performance. At the output, steady state performance is what? The output of the system at t equal to infinity, isn't it? That is your desired value you are looking for. You are going to apply something and you want to get some out from the system, isn't it? You are not interested in transient behavior, what the system is going to do inside. No. If you switched on, the fan should be rotated or not. Okay. So the steady state performance of any system should be perfect. Perfect means the steady state error should be very less. So the transient behavior is less important than a steady state performance, and the steady state performance is going to increase by lag compensator. Okay, that's why note down one thing: all practical control systems are low pass filter. They are not high pass filter. They are low pass filter. Note down this point. Okay, all practical control systems. The next point is, with lag compensator, the system becomes very sensitive with respect to parameter variation. So the system will become very sensitive with respect to parameter variation. This is another important point related to the lag compensator. And the next one is the LGF, not LGF, it's LGC. The lag compensator is similar to PI controller. We'll see later what is the PI controller, but PI controller is the Y of lag compensator. Okay. The very next point is Jai Hind, Jai Bharat. Chaliye, for today's class it's enough. We'll meet in the next class with some problems. Then we'll see leg lead and lead leg. So up to lead and leg, these two are very important. You have to remember there are so many questions in the examination from this background. If the EC people, if you'll observe your previous year papers, you have total 17 questions. 17 questions. Instrumentation people, you have questions more than 17, and EE people, you are near around 20 questions. So please, if you are practicing, for EC people I'm telling, so practice the question of the instrumentation and electrical fellows, you will do the same thing. Instrumentation fellow, you will do the same thing. There is no need to take questions from here and there. Previous year papers of 3 branches are more than enough. Okay, when you will give the gate examination, when you will come out from the center, you will realize my words there, that whatever I'm saying here was correct. You will think there. So friends, we'll meet in the next class. Till then, Jai Hind, Jai Bharat.